I will be using the acoustic wave equation here, although these concepts can be applied to EM waves also, because the way the wave equation is written is the same for both the types of waves. Okay, although there are additional concepts in EM wave propagation like polarization and all that, we don't deal with that here, but still some of these concepts can still be applied there. Okay. So what do I mean by concepts in wave propagation? Okay. So the wave equation, I call it, is this: del square p is equal to 1 by c square d square p by dt square partial. Okay. Now p is the pressure wave. Okay. Now the question is, what do the solutions to this wave equation look like? Okay. Okay, meaning what are waves basically? Okay. The other question, or rather the concept, is concepts of wave interference, phase velocity, phase or slowness, group velocity, or slowness, spreading. Okay. Also, that's about it. Okay. Okay. So before we look at these concepts, we derive the math behind them. Okay. There is some background that's required. I'm not going to go a lot into the background that's required, but just to alert you to the different concepts that we will use here. Okay, if in case you need, you could go look up a textbook on it. But what is the background that is required before we deal with this guy? Okay, first one is complex numbers. Okay. Okay, specifically, you want to write harmonic waveforms. Okay, you could write exponential of j times omega t, where j is the square root of -1. Okay, that is the square root of -1, right, plus j times sine omega t. Or you could write it in another form. You could say your sine of omega t is imaginary part of e to the power j omega t, and the cos of omega t is the real part of e to the power j omega t. Okay. So that's some background that you'll need. Okay, and there's some more that you'll need, which we will do. Right, continuing with the background that's required. Okay, you will also encounter the concept of the impulse function. Okay. Now, what is this impulse function? Okay. The impulse function is denoted as this. You write this little delta here and of the argument t or x or u, whatever you want to take it. Okay. We will have a value of infinity at t equal to 0, and will have a value of 0 elsewhere. Okay. However, your integral delta of t dt is equal to unity. Okay. And it is depicted, okay, by something like this. Put this, you put a 1 next to it, and let us say this is t or x. Okay, as it is so concentrated along t or x that it is infinitely small. So you could think of a stretched out rectangle, okay, that's getting compressed further and further. So it's getting bigger and bigger and bigger, and so it gets infinitely tall, but also infinitely small at t or x equal to 0. So that's the concept. But although it is infinity at t equal to 0 and 0 elsewhere, we have this thing where we can, this saves us, and I say that you integrate delta of t dt from minus infinity to plus infinity, you get a value of 1. Okay. All right. So, we will use that later to illustrate the concept of an impulse propagating. Okay. Then there is the concept of the Fourier transform. Okay, where we write your f of omega, we have a measurable function f of t. Okay, you could write this as e to the power minus j omega t dt minus infinity to plus infinity. Okay, so given your f is measurable in the Lebesgue sense, okay, then you could decompose your f of t into complementary frequency axis omega, okay, and you could decompose it into its omega components. F of omega is equal to f of t e to the power minus j omega t dt integrated. Okay, and you could go the reverse direction. If you have the frequency content of the signal, okay, you could write it like this. All right, the f of omega. Just know that if you put minus j omega here, you put plus j omega here. There's plenty of literature on Fourier transforms, how they derived, their existence, etc. Okay, well, I'll leave it here. You can look it up. Okay, all right. So now let's go into the solutions to the wave equation. Right, as I said, what do the solutions to the wave equation look like? Okay. Okay. Now you have this, your del square p is 1 by c square d square p by dt square partial. So, this is your wave equation. Okay. Now, this operator del square, I am going to write it in the Cartesian coordinate system, okay, and we get del square is d square by dx square partial plus d square by dy square partial plus d square divided by dz square partial. Okay. So, I plug this in to here, right, I will get this, which is d square p divided by dx square partial plus d square p divided by dy square partial plus d square p by dz square partial equals 1 by c square d square p by divided by dt square partial. Okay. Now, let us simplify this. Okay, let us consider the solution to this in the easiest manner possible. Okay. Let us say that your pressure wave, your wave does not vary along the y and the z direction. Okay. Assume your dp by dy is equal 0 and then your dp by dz partial also equal 0. That implies, okay, okay. Now, this you could say is there is only x and t term, right. So, you could say that this wave only propagating along the x axis. Okay, all right. Now look at this guy here. Let me see. Yes. Right. Now just look at this guy here. Right. Okay. What can the possible solutions be? Right. So, if you look at this, right, one solution, a very general one, right, is this P equals f of c times t minus x, right. So, you take this guy here, right, and then plug it in to this one dimensional wave equation. Okay, you will see that d square p divided by dx square partial equals 1 by c square d square p divided by dt square partial. You could plug it in, do the differentiation and check for yourself. Okay, right. Now, let us look at this one a little bit more. Okay. Now, what this says is your p, right, depends on the argument to f, which is Ct minus x. Okay. So, you could have different values of t and x, but it does not matter as long as your argument c times t minus x equals the argument c times t minus x at another time. What I am saying is, you could write your p is equal to, let us say I could call this p1 and then I write this as c times t1 minus x1, okay, and then say I sample the waveform at another time t2 and another coordinate x2, right. I could have p1 equals p2, which would imply that your and this implies your c equals x2 minus x1 divided by t2 minus t1. All right, there you go. So, your waveform f propagates, it travels at a velocity c. All right. Okay. Now, because of the way the wave equation is, right, if p equals f of Ct minus x is a solution, then p equals a times some a is some value, some quantity. Okay, a times Ct minus x is also a solution. Okay, you could go even further, and you could write if so is p equals a times f of Ct minus x plus b times, you could add them up together. Okay, so you could write b times g of Ct minus x, right. So these are also solutions. Okay, so there is a linearity that waves satisfy. So we have wave 1 being a solution, you have wave 2 being another solution, you could have wave 1 plus wave 2 also a solution. Okay, so that's what I'm saying. It will come in handy later. These properties will come in handy as we go along. Okay, now in going forward, I'm going to change things just a little bit and write the wave equation as this. This is the left hand side of the wave equation that we had, okay, and on the right hand side we had this guy d square p by dt square partial, then divided by c square. I'm going to write it as s square, okay, where s equals, sorry, not s, just a minute. Okay, where your alpha is the reciprocal of the velocity, and this alpha is the magnitude of slowness. Okay, so you have velocity before for c, you have the reciprocal of c, and that we call as slowness. Having things in terms of the slowness and the slowness vector simplifies things as we go along. Okay, so well, it hasn't complicated things that much, the math. Okay, now if you look at the solutions for this, it allows us to write p is equal to f of t minus alpha times x is a solution. Okay. Okay. Now we'll be looking at this more. Okay. All right. Now let us see what this thing looks like. Okay. Now to make things easy, I'm going to write your f of t, right, or rather I'm going to write it as f of u, right, the waveform is your impulse function delta of u. Okay, all right. Okay, so then what does it look like? Okay, so now if you have your p, right, is delta of t minus alpha magnitude times x. Okay, all right. So now let us try plotting it. All right. Okay. So you have this. Okay. What is this? This is your y-axis, and this is your x-axis. Okay. So it is going to reach this impulse, right? I'm going to first plot this on the xy plane, okay, and to just show where the impulse is, I am going to use just a dot, okay. Okay. So, first thing that you will end up getting is at x equals t divided by alpha, it is going to reach here, okay. And then in going forward, right, at x equals 2t by alpha, it is going to get here and it is going to get here, okay. Now, let me write this down, okay. This one is 2t divided by alpha, this one is 3t divided by magnitude of alpha, okay. Now, what about the other points on the xy plane? When is the impulse going to reach there, okay? Well, that's quite straightforward, because if you look at the expression that we have for p, right, it is progressing along the x direction, okay, and it has the same value, does not vary along the y, right. So, what is going to happen is, if you were to plot the position of the impulse function, right, along the y axis here, right, if you fix x here and you went up, right, so you will get at the same times you will get this, right. So, you get this, you get this, you get this, you get this, get this, get this, you get this, and it keeps going, okay, right. And the same thing for the next time instant, if you were interested in where does this impulse, right, if I take a line along the y axis, right. So, it keeps going like this, keeps going like this, going like this, 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 okay. Oh, sorry. Okay. Now, okay. Now, this line here, right, this thing here, right, where that denotes the position of the wave is called as a phase front. Now, this is another phase front, okay. The argument of your pressure wave, this t minus alpha x, right, it's constant here, right? So, this is again called your phase front, okay. So, that's your concept of the phase front, okay. Now, we could do the same thing for a slightly different case of the wave equation. Okay. Now, we could write, yes, okay. Okay. The wave varies along x and y, it does not vary along z, to keep things simple, okay. Now, the solution to this equation is going to be say f of t minus alpha vector dot x vector, x position vector, not this x, okay. Now, what is this? This is f of t minus cos of alpha minus okay. Now it's propagating along x and y. So you have a slowness vector that has an x component and that has a y component. Okay. Now how would this look? Say again, let's take the impulse function. F of u is delta of u. Okay, and let us assume that your let's fine. Let's assume that your alpha is pi by 4. Okay, so you have p equals delta of t minus alpha vector x divided by square root 2 minus alpha vector y divided by square root 2. Okay, all right. So what is this one going to look like? Okay, let us see. This is your y. Just a minute, let me erase this thing. Okay. Now this is your x and this is your y. Okay. Now let us say at t equals um, 0, right? So at t equals 0, t equals 0, right? Now if I did the same approach and if I were to plot the position of my impulse along different points of the xy plane, and what would it be at t equal to 0? I would get this line here, which would just go through the origin. Okay. Okay. So this is what it is at t equal to 0. Okay. And now let me, right. So this one is this guy t equal to 0 phase front. Okay. Now at t equal to some value capital T, let's say P equal to delta of T minus okay. Now what is this guy going to look like, right? So you're going to get this, I think. And at this point, this one. Okay, and then in advancing it further, say I take t equals twice capital T, then I get this. So this is how the phase friends propagate away from the origin as you advance in time. Okay. Okay, now this guy is t equals capital T. So this is some t. Yeah. Just a second. Just let me just. This is going to be and so on. Okay, so this one is going to be 2 times ct square root 2, and this one is going to be 2 times ct square root 2, and so on. Okay, so let me write it here. Okay, or rather, let me use a different. Okay. Okay, so that's how your wave propagates. Okay, now, all right. So now let's shift gears a little bit and go into harmonic waveforms. Okay, and for that, let me write this, right. Harmonic waveforms solutions to the wave equation. Okay, now we have this. Right. Now, could use something called the separation of variables approach, and you could suggest a solution for this, and then we write your just a minute. Now we know that the pressure wave is a function of x, y, z and t, and they come as separate terms. So, we could write this as f of x g of y times h of z times p of t. Now, you plug this in to here, right, and what you'll end up getting is something like this, where you'll see that you can write your p of x, y, z, t, okay, is e to the power j times omega t minus this wave number vector k vector times dot product of a position vector x, okay, where your position vector x, right, is x, y and z, okay, all right, okay. You could go through the steps and see it for yourself. Some people will write the solution in terms of sines and cosines. They'll write solution to the wave equation is sine of omega t minus k vector dot x vector. You will get the same thing here. If you take the imaginary part, if you want the cos, you could take the real part, okay. So, you could do all that, all right. Now, are there imaginary waves really? No. No, so there are no imaginary waves, okay. So, wave propagation is a real phenomenon, okay, for acoustics, and so this is using complex exponentials, okay, is a tool for mathematical convenience, okay. Now, so this is what it is, okay. So now the slowness vector, so you could write this as e to the power j omega t minus alpha vector dot x vector, because it introduces slowness vector. Now, what is the slowness vector here? Now, your slowness vector is alpha vector is k vector divided by omega, okay. Now, this is called the wave slowness, okay, and you could write your also, right, your omega by k, right, is the what is it? It's is the wave speed, okay, or call it celerity, or call it as phase speed, okay. Now, this quantity here, right, this k, right, is 2 pi by lambda. It has units of radians per meter, dimensions of L to the power minus 1. This is what is called as the wave number. Just like how we have angular frequency in time domain, you have this one. You have this wave number for the spatial domain. Okay. Now, you have this. Okay. Now, what is the big deal about this, right? So, why should we care about this? Okay. Now, it turns out that the complex exponentials are useful building blocks from which we can build more complicated waveforms. Okay. Right. Now, the theory of Fourier transforms tells us that you can have your S of x, because waves satisfy the property of linearity and addition, right. So, you can have your S of x vector comma t as this. So, you could use these, you could add them up, I could add up these different solutions of your wave equation, weight them with S of omega, right, and you could create more complicated waveforms. Okay. What is this S of omega? S of omega is the Fourier transform of another measurable function s of u e to the power minus j omega u du. Okay, all right. Now, why should we care about this, right? So, this generalizes the solutions to the wave equation to a much larger class of waveforms. Okay, we don't care whether the signal has to be an impulse, should it be a complex exponential, should it be a sine waveform, should it be a complex wave, or should it be a cosine waveform. Okay, all that we care about is the waveform measurable. Okay, and then we have the Fourier transform telling us that you could incorporate any such waveform such as triangular wave, square wave, you could have a step wave, right. So, you could have all those kinds of waves and they are all legitimate solutions to the wave equation, okay, because you could write them as the sum of complex exponentials, right. Okay. So, all of these are equally worthy solutions of the wave equation, all right. Okay. Now, what I have not done here fully and is you could write the solution to the wave equation in the cylindrical coordinate system can be written in the cylindrical coordinate system by writing your by expanding your delta square as 1 by r d by dr partial r times d by dr partial plus 1 by r square d square by d phi square, where phi square is the azimuth, and d square by dz square. And by expanding your del square not in the Cartesian coordinate system, but rather the cylindrical coordinate system, you get a different type of wave solution. Okay, and what you end up getting there will be something like this, where you get p is equal to 1 by square root r, okay, e to the power j, okay, omega t minus k r. Okay, while you may be familiar with this guy here, right? There's a time variation, there's a range variation, okay, there's angular frequency, there's wave number and all that. The thing that's new for us when we write the solution to the wave equation in the cylindrical coordinate system is this guy here, okay. Now, this one suggests that the wave is going to spread, okay, that its amplitude is going to go down as a function of 1 by square root r as it propagates farther in range. There is no such spreading in the plane wave concept, okay, but in the cylindrical coordinate system you do have that, okay, all right, and right. So, that's the main thing. But also note that you have r here, r is a radial distance, okay, there is no x and y here, it's all the radial distance, okay, all right. Now let us write it again. Similarly, I'm going to write here for spherical coordinate system. I'm not going to expand the Laplacian operator in the spherical coordinate system here, but you can look it up. I'll just write the solution to your wave equation. One divided by r. Okay. Now, what is different here? you have the same radial distance, okay, r, oh, sorry, sorry, same radial distance r, okay, but the your amplitude is now going down by a factor of 1 over r. For cylindrical coordinate system, it was 1 over square root r here, but here it's 1 over r. Okay, it goes down quicker. The amplitude goes down quicker in range in comparison to your cylindrical wave. Right now, these concepts of spreading are important when you derive, say, or calculate what is the transmission loss that is expected, what is the power loss that is expected when a signal propagates a distance r, and so on. Okay. Now, now the other concept is wave interference. Okay, and for that, just to keep things easy for us, I'm going to write things in terms of sines and cosines. Okay, now let us say you have two waves. Just a second. Okay. Okay. So here y1, right? I'm going to use cosine wave here. Okay, y1 is cos of omega t minus k1 x. Okay, and then I'm going to have y2 is cos of omega t minus k2 x. Okay, now the question is, what is y1 plus y2? Okay, all right. So assume, just to make things easy for us, we're going to assume that your t is 0, right? And what we want to know is, what is the resultant amplitude of the summation of these two signals here, and how does it vary across the range x. So y is equal to y1 plus y2, and that will get you cos of k1x plus cos of k2x. Okay. Now, to simplify things for us, we are also going to write, assume your k1 and k2 are somewhat close to each other by writing k1 is k plus delta k by 2, and k2 is k minus ups. Right. So y equals cos of k plus delta k by 2 times x plus cos of k minus delta k divided by 2 times x, right? So what do we have now, right? You have a cos of a plus b is cos a cos b minus sin a sin b, right? So you expand things out in that manner, and what you'll get is, if you expand this guy and if you expand this guy, what you'll get is 2 times cos kx then you will get All right. Okay. Now, this is not a very, there are not that many more steps left in the solution. I'm going to continue it, this thing here. Okay. Now, what is this, right? So, if you look at, let me write it here, 2 times cos of kx times cos of delta k by 2x. Okay. Now, say, as I said, the wave numbers are different, k1 and k2 are different, but not that much. So, I can write, say, cos of delta k is um, is much smaller than your k, right? So then what happens is your amplitude of y, right, is going to be this guy. It's approximately cos of delta k divided by 2x. Okay. Now, if delta k equals 0, okay, then I'm sorry, let me put this times 2 here, 2, right? Then that implies you is going to be twice the amplitude. You had amplitudes of 1 and then just a minute. You have amplitudes of 1 here and then you had an amplitude 1 here, but now delta k is 0, you had twice the amplitude. Okay, and then if what is if sorry, just a minute, sorry. Right, so that okay. If your delta k by 2 times x, right, is equals n times pi, then here it's going to be twice the each of their amplitudes that added up. Okay. Now this is called constructive interference, right? Now instead, if you have the two waves being out of phase, okay, but is equal to pi by 2 and further multiples, then the locations at which you have this equal to 0, and this is destructive interference. Okay, right. So that's concept of wave interference, where you have two waves that differ in phase, they add up. If they are in phase, the amplitude of the resultant goes up. If they are out of phase, they cancel out each other. Okay, that's what it is, right? And the amount of, or rather, how often the constructive interference effects and destructive interference effects happen, right, across x will depend on the phase difference delta k. Okay. Now you could do the same thing for interference in time. You could fix x and you could see what are the points at which they constructively interfere and destructively interfere, right? and you'll see that it will depend on what is the frequency difference between the two waves that are interfering with each other. Okay, all right. So now let me write tell you the next concept. Okay, okay. Now going to do this concept of group velocity. Okay, okay. Same thing. We're going to consider the resultant of two waves. Okay, and just for fun, I'm going to switch things, and I'm going to switch back to the sine waves. Okay, and I have two different frequencies. Okay, and also the wave numbers are also different. Okay, okay, plus okay sine of so you have the wave numbers varying across frequency. Okay. Okay. All right. So now, if you do the summation, what you'll end up getting is 2 sine of omega naught t minus some k naught x times cos waveform. Okay, delta omega by 2 times t minus delta k by 2 times x. Okay, right. So what's happening is you have a fast varying waveform in time sine of omega naught t minus k naught x. Okay, and then there is this thing that is the slow varying envelope. Right, because delta omega is much smaller than your omega naught. Okay, and this envelope which carries the amplitude information. Okay, now if you look at the phase of the envelope, okay, and use that for your phase front calculation. Okay, and that is going to travel at the rate I'm going to call Vg, because the group of waves, two waves here, Vg is equal to x by t, and that is going to be your delta omega by delta k. Okay, now this guy here, okay, let me write this again. Sorry. I'm going to call this okay. Now this guy here is called the group velocity. Right now, this concept is very important wherever you have dispersion of waves. Okay, where the wave number varies as a function of frequency. So you could have different frequencies traveling at different group velocities, and then you have something called as chromatic dispersion, because different frequencies have different speeds. So you'll see that as they propagate farther and farther in range, they're going to come at different times, and the time spread is going to increase. So the arrivals are further and further dispersed as they propagate along, and that's because of dispersion due to this group velocity phenomenon. Okay, all right. Thank you.